Hello, my name is Peter Brown. I'm a postdoc in Doug Shepard's group at Arizona State, and today I'll give part one of our workshop on high-quality 2D SIM reconstruction in Python with our mcSIM package. In part one, I will discuss SIM and SIM reconstruction theory. I'll begin with an introduction to the technique of SIM. Then I'll discuss requirements for performing high-quality SIM and assessing the quality of your SIM data. I'll discuss the SIM reconstruction algorithm in some detail, as well as parameter estimation as input to this algorithm. And finally, I'll discuss combining optical sectioning with super resolution. There will also be a part two to this tutorial given by Doug Shepard, where he'll give some examples of how to use our mcSIM package, using some Jupyter Notebook examples that you can download, and reconstructing data from our homemade DMD SIM instrument, as well as a Nikon InSim commercial instrument. So briefly, structured illumination microscopy, or SIM, is a family of techniques that obtain super resolution information from a sample by projecting structured light onto the sample and taking advantage of a frequency mixing effect. And so on the left here, I'm illustrating this frequency mixing effect. If you imagine one of these grading patterns is our illumination pattern and the other is the sample, you can see when we multiply the patterns together, we see a low frequency, long length scale pattern emerge that's not a property of either of these individual patterns. This effect is referred to as the Moiré effect, and it's an example of frequency mixing where we're looking at the difference between the dominant frequencies in these two patterns here. This is the essence of SIM. The other important concept is that we think of a microscope as a band-limited system. So in some sense, a microscope is a low-pass filter that can only measure spatial frequencies that are below some maximum frequency. And so the advantage of a frequency mixing technique is we can translate very high frequency information that's above the bandpass of our optical system down below our maximum frequency where we can detect it. This Moiré effect is not restricted to these grading patterns that I'm showing on the left, but is extremely generic. For example, in the middle, I'm showing you a series of hexagonal patterns, two superimposed hexagonal patterns, which exhibit the same kind of lower frequency information. We can think about this with a very simple mathematical example. If we multiply two sine waves with different frequencies together, we get a signal at the difference frequency between these two sines, which is exactly this Moiré pattern, this low frequency pattern that we showed here, and a signal at the sum frequencies, which will be removed. It won't make it through the bandpass of the microscope system. In the simplest instance, we generate a SIM pattern by interfering two laser beams with a lens. So this is a simplified schematic of what's going on in SIM. Our two beams interfere, and then we would put our sample here, and all of this frequency mixing information would then be contained in our image. SIM was initially realized in roughly the year 2000 by several different groups, although these ideas that I've presented here dated back much before that. So how does this work a little more explicitly in our microscope system? Well, if we now imagine one of these gratings is a specimen of interest and the other is our illumination pattern formed by this two-beam interference, then we can look at the microscope bandpass function in spatial frequency space, which is shown here in figure B. The region in blue is the region the microscope can detect. Now we project a SIM pattern at some spatial frequency K1, which can be close to the edge of our optical transfer function, so near this bandpass. And then from the frequency mixing effect, we get information not only about this band-limited region of the sample where we would also get information in wide-field microscopy, but also these two other regions displaced here by frequency K1 coming from our moire pattern or our frequency mixing. Now, this information from these three bands is all mixed together in the image, and so we have to unmix it somehow. We'll discuss exactly how this works later, but we'll find it is necessary to shift our illumination pattern's phase and typically take 3 different images to extract this information. You can see also from the single pattern, we're getting information along, or super resolution information along one direction of the sample only. So if we want to obtain an isotropic super resolution image, then we will have to rotate our pattern in addition to doing the phase stepping. So typically, doing SIM imaging, we need to take 9 images using 9 slightly different patterns. From this picture, you can also see that SIM is limited to giving us twice the resolution of the wide field microscope. How does this look in an experiment? Well, here's a figure from one of these early papers. In panel A, you can see the spatial frequency spectrum of our wide field image. And B is a raw image from the SIM. You can see out here, we have a peak coming from our SIM pattern, and this is mixing additional spatial frequency information into our picture. You can see some of it here. If we unmix this information computationally, then we'll obtain these separated frequency bands that are shown in C. And finally, we need to combine all of this information to form our super resolution image. As I mentioned, we're typically working with 2-beam interference to form our SIM patterns, although there are other varieties that use different schemes. And there are many different ways to generate these types of interfering beams. In the early SIM experiments, this was done using diffraction gratings that could be translated and rotated to change the patterns and generate the different patterns that you need to do the reconstruction. To improve the reliability of this process, as well as increase the speed and enable various other advantages, a number of different technologies have been applied to ReliSim in the years since. One very prominent example are using liquid crystal on CMOS spatial light modulators to generate your SIM patterns. Interferometers can also be used, as well as digital micromirror devices. Recently, there's been interest in using fiber arrays to generate SIM, as well as photonic chips, and various other technologies that I haven't discussed here. SIM is also a very flexible idea, since the essence of it is simply applying a structured pattern and relying on frequency mixing. You can imagine there are many different ways to do this and to potentially get more information out of the process beyond the 2-dimensional SIM that we've discussed so far. For example, if we use 3 beams, we could do 3D SIM and get super resolution along the optical axis as well as transverse to it. There are other 2D SIM techniques that, instead of using 1-dimensional sinusoidal patterns, rely on lattice patterns, for example, hexagonal patterns. Finally, there are nonlinear SIM techniques that can expand the super resolution information that you get beyond a factor of 2 times the standard resolution limit. Since SIM is so flexible, we can also combine it with a variety of other approaches. So here's just a small sample of some of those other areas that SIM's been applied to. We won't discuss those in detail, though. And finally, I should say that SIM is a popular super resolution technique because it makes relatively few requirements on your samples compared with other approaches. For example, it doesn't require any specific photophysics. It's not a scanning technique, so it can also be quite fast. If we're taking roughly an order of magnitude more images than wide field, so the speed is only a factor of 10 slower, which means you can do things like live cell imaging potentially, which are challenging with other super resolution techniques. So today we're not going to discuss any of these other various applications of SIM. We'll focus only on linear 2D SIM and doing linear 2D SIM reconstruction. Now that we've introduced the concept behind SIM, I'll discuss some of the requirements for generating high-quality SIM data and also for assessing the quality of SIM data that you've already generated. The most important quantity for determining if your SIM data will be high quality or not is the modulation contrast value. A typical SIM pattern looks like this. This is the type of cosinusoidal or sinusoidal pattern we've already discussed. And the important parameters here are the frequency, the phase, and this modulation contrast value, which can range between 0 and 1. And so this gives you important information about the pattern. When the modulation contrast is 1, that says that in the troughs, the SIM pattern will approach 0. Well, at its peak, it will approach some maximum value. And what's critical here is we actually have places where the intensity goes to 0. On the other hand, in a low contrast pattern where M is less than 1, we no longer have these areas where our pattern goes to 0. The mean of the pattern is the same, but the amplitude of the modulation has greatly diminished. This is a critical parameter for controlling the signal to noise that you achieve in SIM, and very sensitive to a variety of possible defects in your system. So it's critical to keep this number as high as possible, and I'll discuss a few of the experimental challenges to doing this in the next few slides, and then we will relate this number back to the signal to noise ratio in SIM and discuss how to get a handle on this and use that to evaluate your SIM data. One of the effects that can really limit the modulation contrast in your system is a high numerical aperture polarization effect for p-polarized light, if you have any p-polarized light in your SIM setup. So here I'm illustrating two SIM beams that are refracted by an optical system and then interfere in your sample plane. If we have p-polarized light for these SIM beams, the angle of that polarization tilts when the beam refracts, and these angles tilt differently for the two beams. And that means when the beams interfere, the contrast of that interference, and therefore the modulation contrast, is reduced. And we can calculate this factor based on the angle this beam makes with the optical axis, which we'll call theta here. And so the modulation contrast for p-polarized light will show some dependence that looks like this. And so in particular, for theta of 45 degrees, you see the modulation contrast would vanish entirely. On the other hand, for S-polarized light, the polarization does not change when the light refracts, and therefore the modulation contrast remains high. We can look at a plot for this contrast function versus the phi, which is parameterizing the polarization of the light. So here for plus or minus pi over 2, we have S polarized light, where for 0, we have P polarized light. And this plot is for theta of something like 65 degrees. What this means is in a SIM instrument, we always need to control the polarization because we're not simply using a single pattern along one direction, but rather 3 different SIM patterns along 3 directions. So when we rotate the pattern, we need to rotate the polarization. A further complication comes from the dichroic mirrors that we typically use in a fluorescence microscope. Dichroic mirrors will give different phase shift for reflected light, depending on whether it's S or P polarized. And so if you start with an arbitrary linear polarization of light reflected off a dichroic mirror, generically it becomes elliptically polarized, meaning you have an S and a P component here, which will cause a decrease in your signal contrast. A nice approach to remove this limitation in SIM systems is to use a pair of dichroic mirrors that are oriented at 45 degrees with respect to each other. So light that is S polarized with respect to one mirror would be P polarized with respect to the other. That means whatever incident polarization you send, we'll see one phase shift. The S component will see one phase shift from the first mirror, and then a second phase shift from the second mirror, whereas the P component will receive those phase shifts in the opposite order, so you'll preserve your polarization and therefore your modulation contrast. Another important effect that can limit your modulation is the coherence of the light that you project onto your sample. So in particular, if we have coherent light, it will diffract off whatever modulator we're using to generate our patterns, be it a diffraction grating, DMD, a spatial light modulator. And then this light will travel through the system according to the coherent transfer function. And so in an ideal case, it will be unattenuated. The beams will interfere and we'll have modulation contrast of 1. Contrast this with the situation where you use incoherent light, such as from an LED. In this case, to propagate the light from our modulator to our sample, we have to use our incoherent propagation techniques, and in particular our optical transfer function. And so the optical transfer function will attenuate the SIM frequencies compared with the DC component, which will effectively multiply our modulation contrast by the value of the optical transfer function at the SIM frequency. In the case of optical sectioning SIM, where we're using a low frequency pattern, this is not so important, but in super resolution SIM, where an aggressive pattern may use 90 to 95% of the maximum frequency of the system, the value of the optical transfer function here can be on the order of 1 to 10%, and so this is a substantial hit. To illustrate this effect, we've simulated both coherent and incoherent SIM using this pattern that consists of a pair of line pairs, progressively greater spacing. You see in the coherent SIM, we can see the moire pattern by eye, whereas in the incoherent SIM, due to the reduced modulation contrast, we can no longer see it. We can look at how the SIM reconstruction changes versus signal-to-noise ratio. At the lowest signal-to-noise ratio we looked at here, the incoherent SIM is not capable of resolving these two line pairs because there's too much noise, well, as the coherent SIM can nicely resolve these. And as we increase the signal-to-noise, at some point the incoherent SIM can resolve the line pairs, but the coherent SIM is always doing a better job because it has this greater modulation contrast. So how do we think about the signal-to-noise ratio in SIM? In wide field microscopy, we're used to thinking about the signal as the number of photons that we collect, and the noise is coming from photon shot noise on the signal, as well as camera readout noise, which is typically a smaller effect. In SIM, the situation is similar, but there's an additional signal that we have to think about, which is the moire pattern signal that's giving us the super resolution information. So here the signal is not the total intensity that we capture, but rather the difference in the intensity between SIM images after we've stepped our phase pattern. And depending on the situation, this can be smaller than even significantly smaller than the total intensity of the image, particularly if you have, for example, out of focus background light in your system. And so we quantify this with what we'll call the modulation contrast to noise ratio that I'll discuss in more detail shortly. Of course, in SIM, we have the usual trade-offs that are common to all fluorescence modalities, where we have to think carefully about what we want to achieve, because if we use a higher light dose to increase our signal to noise ratio, this can reduce the, for example, the temporal resolution or the amount of the volume of the sample that we can scan, because increasing the light dose will lead to more photobleaching and phototoxicity. Okay, so what is the modulation contrast to noise ratio? This is a quantity that exactly describes the SIM signal to noise ratio. So in particular, if we look at a single pixel in our image, we should be able to describe it as some constant intensity that stays the same as we change the SIM pattern. So for example, the portion of your pattern that's coming from the out of focus background light in the sample, or that's always there because your modulation contrast is not perfect. And compare this to the portion of that light that changes between the images. So the SIM signal that we're going to extract the super resolution information from. So if we want to form our signal to noise ratio, this is twice times the amplitude of this signal. So this would be the peak to trough distance for this term divided by the shot noise of the image. We can express this in terms of the intensities of the individual images using this top expression, which looks a lot like the optical sectioning SIM expression, which it essentially is, and this lower expression, which is just the average of those images. What's convenient about this quantity is it's local, so we could calculate it for each pixel and get a spatially varying sense of where we have high contrast in our sample and where we're likely to get a nice reconstruction. In particular, we typically want a modulation contrast to noise ratio of at least 3. If it's any less than this, we're unlikely to get a high quality SIM reconstruction. This quantity has also been discussed in more detail in a variety of publications, so I encourage you to check these out and learn more about this. In our mcSIM package, we provide a diagnostic plot to help with evaluating the quality of SIM data. We show several things on this plot, including the intensities of the raw images. So here the column represents a single phase, and the rows each represent the different angles. So for example, in this particular data set, we have a signal of about 3,000 photons peak. You can nicely see the moire pattern for this angle, and this is reflected in the modulation contrast to noise ratio over here, which is above 20 for this particular angle, where for the other two angles, it's smaller, perhaps in the range of 5 or so. This also illustrates another important fact about the MCNR, which is it is not a quantity that's purely determined by the SIM pattern. It's determined by both the SIM pattern and your sample spectrum. So the reason that the MCNR is so much larger for this angle compared with the others is because this particular sample has frequency components that are relatively near the SIM pattern, the SIM frequency for this period. And so that means we get a very prominent moire pattern at low frequency, hence it's not attenuated by the optical transfer function. Whereas for these other two angles, there is not much frequency information for the sample along those directions, so we get much less MCNR, even though the patterns are of comparable quality. So a low MCNR can either tell you that your SIM pattern is low quality, or it could tell you that your sample doesn't have a lot of frequency contrast along those angles. In either case, you will not get a lot of extra information from your SIM image. So it amounts to more or less the same thing in terms of the reconstruction. Now that we've discussed how to generate and assess high quality SIM data, we're going to discuss the SIM reconstruction algorithm. At the outset, I should say there are many different ways to reconstruct SIM data. We'll discuss the sort of classic Gustafson, Heinzmann style Wiener filter reconstruction algorithm. This is a relatively simple algorithm that has some known limitations, but some of the primary benefits include the fact that it's a linear reconstruction approach and therefore relatively easy to understand what's going on, easy to understand where artifacts may come from or other issues may arise, and so therefore easy to diagnose these and correct them. But of course, there are other more sophisticated algorithms that use, for example, Bayesian approaches or more optimization-based approaches that can also be very interesting and useful. So the classic Wiener filter reconstruction. We begin with the forward model for image formation in SIM. And as we've discussed before, you have a term that is your object, represented by O here, multiplied by your incident illumination, your SIM pattern, which is this sinusoidal pattern here with modulation depth M, SIM frequency k theta that depends on the angle of the SIM pattern, and SIM phase phi. As usual in microscope imaging, we take this illumination intensity at the sample and convolve it with our point spread function to get the intensity image on our camera. We've discussed SIM already in the context of frequency mixing, so it's very useful to look at what this equation becomes if we take a spatial Fourier transform. In spatial frequency space, this product is converted to a convolution, and this convolution is converted to a product. When we take the convolution of the SIM pattern with the object, we get our frequency mixing effect. And now we have three terms, which we'll refer to as bands, in our image. We have the Fourier transform of our object, which is the same as we would get in wide field microscopy. We have a term that's proportional to the frequency spectrum of the object, but shifted one way by the SIM frequency multiplied by the SIM phase, and another term that's essentially the complex conjugate of that term. That's the object shifted in the other way by the SIM frequency. And then this is multiplied by our optical transfer function, which performs the band limiting, as we've discussed. What's powerful about this equation is we see the intensity that we measure is linearly related to these three different bands. So if we take images at different phase values of our SIM pattern, then we can put together a linear equation, a matrix equation, that connects these bands to the image data that we get. And then finally, we can extract these bands simply by inverting this equation. However, we have an additional effect of there being noise in the problem. So if we didn't have any noise, doing this inversion would, in some sense, give us the values that we wanted for the bands, and we could just add them up as long as we keep in mind the frequency cutoff limitations of these optical transfer functions. In the presence of noise, we need to be a little bit more sophisticated about how we combine these bands. And for this, we use a Wiener filter style combination. So the way that we combine the bands, we take our bands, and then we have to shift them by the proper frequency vector to put the information back in the correct place in frequency space. So for example, this shifted band, we have to add a factor of k theta to move it back to the right place. And so that's exactly what this term is. Next, we can multiply this term by the optical transfer function, which will give us roughly the object times the optical transfer function squared. And then we'd like to divide by that optical transfer function. However, if we did this naively, what we would find is near the edge of the optical transfer function support, where the OTF is going to 0, we're dividing this quantity by a very small number. This is particularly problematic because in the region where the optical transfer function is very small, eventually, at some stage, at some high frequency, we're dominated by noise and no longer by signal. And so at this point, we're dividing a quantity that is essentially only noise by a very small number. And so we would be tremendously amplifying the noise in our system. And so to avoid this, we add an extra term, eta squared, here to our denominator, which limits the amount of noise amplification that we can get in our problem. And so this is exactly, this Wiener filter reconstruction idea. One issue that we'll discuss is a proper way to choose Wiener attenuation parameter eta. And this reconstruction approach has been implemented already in various open source reconstruction software such as FairSim and discussed extensively elsewhere. So there's a lot of information on this out there. And this is exactly the reconstruction algorithm that we implement in our mcSIM package. So just to put this back in the context of some of the experimental data that we've already showed, we start with our raw SIM image, then we perform this band unmixing step. And so for a single angle, we're producing these 3 bands. For the second angle, these 3, and for the third, these 3. And then we perform the Wiener filter to combine these bands into our single super resolution image. This algorithm needs a number of parameters as inputs to work properly. In particular, the SIM frequencies for each angle, the modulation contrast values for each angle, the phases for each angle, the optical transfer function, and the Wiener filter parameter. There are a number of ways to estimate all these parameters, and I encourage you to take a look at some of these papers. But we'll briefly discuss some of the most efficient ways to do this, to estimate, for example, your SIM frequencies from your raw data. For some of these other parameters, such as the optical transfer function, you would want to do an independent calibration to estimate this, for example, from your point spread function or from a pupil retrieval sort of scheme, something along these lines. But these 3 parameters, we'll discuss how you can estimate these from SIM data and how you can choose an appropriate Wiener filter parameter. Just another look at some raw SIM data. Typically what we have are some images of our sample that look like this with 3 phase steps and 3 different angles. And the Fourier transforms look something like this. So here, more clearly than these previous images, you can see the SIM peaks. And the first thing that we'd like to do from these images is try and estimate the frequency of our SIM pattern. A naive way to do this would be to identify the position of this peak in the Fourier transform of our image. And in many cases, this does work effectively. However, it's not a general approach because, for example, in turf sim, you may actually excite your sample with a SIM pattern that's above the bandpass of your system when you measure in fluorescence. And in that case, you won't see these peaks in your image, even though the super resolution information has been efficiently mixed into your image. So one useful way to estimate the frequency is to do an initial band separation by inverting this matrix I showed before. And here you have to assume that you know the phases of your SIM pattern. Actually, this procedure right here is only sensitive to the relative phases between the patterns, which typically you will know at least a good approximation. So assuming that you have an estimate for these, you do the unmixing of the bands, and then you take a cross correlation of your unshifted band with your shifted band, and you look for the maximum shift frequency in this cross correlation. You could do this efficiently with a fast Fourier transform, so this is a pretty easy algorithm to run. And essentially the intuition is if you look at these shifted bands, well, the first band is essentially your wide field information. Well, your second band has been shifted by your SIM pattern frequency. So if we set our K naught equal to that SIM pattern frequency, then we're just taking the absolute value squared of your object spectrum. Whereas at any other frequency, we're adding up different points in the object spectrum, and so we'll be averaging over some essentially random phases, and so we expect this to be small for other frequency values. So we've implemented this in our mcSIM package, and here is a diagnostic plot that we show illustrating a typical cross-correlation pattern in this upper right figure between our two shifted bands. Here we show a zoom in around the particular frequency of interest. And we blow this up over here in this upper left plot. And so you could see we're able to nicely identify a peak, which is representing the SIM frequency. It can also be useful to look at the power spectrum of these individual images as well, where we will frequently also see peaks, although of course the only image that we necessarily need to see a peak in is this cross correlation image. Having estimated the SIM frequencies, we also would like to estimate the phase steps and the modulation contrast. We typically can also do this by looking at the separated SIM bands. One approach to estimating the phase that was introduced by Wicker and collaborators is to choose some guess for our phase shifts, unmix the bands using the inverse of the mixing matrix we discussed before, and then look at the correlations between the bands. Since the bands have an overlap region, they will exhibit a strong correlation when the phase unmixing angles are correct. So you can then write this as an optimization problem. And what you find is this approach works very well, even at low photon numbers, so very noisy signals. In fact, the natural thing to compare this approach to is if we were to just take the phase of the SIM peak in the Fourier transform of our data image. And of course, that SIM peak will have a phase that's related to the SIM pattern, but in addition, there will be signal at that same frequency coming from the object spectrum as well as noise that can change this phase somewhat from the actual SIM pattern value. And so in that case, just looking at this peak phase will not give you the correct angle, but looking at this correlation still will. So similarly, we can estimate the modulation depth from looking at these separated bands, because if you have your two separated bands, again, these should be equal in their overlap region up to a factor of your modulation contrast. This band can be weaker if the modulation contrast is less than 1. So by looking at the ratio of these bands in this region, you can estimate this value. So here, this is showing you that indeed, for these two bands, you see the same structures in the bands in the overlap region. Next, we'll discuss how to set the Wiener parameter for your reconstruction. We discussed briefly some intuition about why the Wiener filter works previously, but there's also a more mathematical reason, which is you could prove that the Wiener filter is the linear filter that minimizes the difference between your reconstructed signal and the ground truth value in the least square sense. However, when you do this, you find a particular value for your Wiener parameter, which is 1 over the signal to noise ratio. So thinking back to our Wiener filter expression, where the signal to noise ratio is high, eta approaches 0, and we're simply dividing our signal by the optical transfer function. Where the signal to noise is very low, eta becomes large and then efficiently cuts off the noise amplification process that we discussed before. However, it's not easy to implement this ideal eta because, as you could see, to estimate the signal to noise value, we need the actual signal value, which is what we're trying to reconstruct to begin with. So this is why typically in SIM reconstruction, we set eta in a phenomenological way instead of using this more principled approach. Although that's not to say there haven't been attempts to estimate the signal to noise ratio in a more principled way. And these can also be very useful. But one useful way to estimate the Wiener parameter phenomenologically is either to have some estimate of your signal to noise ratio or to vary the Wiener parameter and look at the quality of your reconstruction versus that parameter. And what you'll see is for a small parameter, you'll get a lot of noise amplification, which you could see at the edge of the region of support in the Fourier transform of your image. And in the image, this will manifest as this high frequency noise that's sometimes referred to as hammer stroke. As we increase the value of the Wiener parameter, the noise amplification at the edge decreases and the hammer stroke also decreases. At some point, we seem to have a quite reasonable compromise where we have very little hammer stroke, very little noise amplification, but still a nice resolution. So for example, resolving this line pair here. If we increase the Wiener parameter further, then we start to attenuate these high frequency regions and to limit the resolution. degrade the resolution of our reconstruction. And so you can see that as we increase this parameter further, we're getting less contrast between this line pair, and in fact, less brightness overall for some of these line pairs that have significant contributions from the high frequency regions in our sample. Apologies, in my previous recording of the session, my microphone cut out about here, so we will pick up the last couple slides in this section. We were talking about selecting the Wiener parameter most appropriate to reconstructing your data. And so we had just looked at some SIM reconstructions of these simulated line pairs versus Wiener parameters in the reconstruction. Now we're looking at our MC&R diagnostic plot. Again, showing you the raw SIM images. You can see the maximum photon number is something on the order of 100 photons here, and we're achieving a nice modulation contrast to noise ratio of over 10 on this data. It's also useful to look at our band diagnostic. And so what I'm showing you here are, for a single image, the Fourier transforms of the images at the different phases. You can see in these raw images, we have our 3 bands mixed together. In the second column, I'm showing you the bands after separation. So you can see the unshifted band as well as the shifted bands. And then the bands after they've been moved to the correct place in Fourier space. These right 2 columns are diagnostics giving you information about the Wiener filter. So this column titled WK is actually the optical transfer function. We're calling it a weight here. This is slightly more generic. You can run this code also with a mode imitating the OpenSIM package, in which case this weight function has a slightly different form. And then this final column, I'm illustrating the effect of the Wiener filter on, or that will be multiplied by each of these bands to construct the final image. Now, briefly, I'll discuss some of the reconstruction artifacts that are commonly seen in this sort of SIM reconstruction approach. We've already discussed hammer stroke, which could become prominent if your Wiener filter parameter is too small. Another set of common reconstruction artifacts include ringing, undershoot, cross-hatching, and honeycomb pattern. And each one of these artifacts is characteristic of certain defects in the choice of SIM parameters. So it's important to learn what each of these artifacts indicate. So we've already discussed hammer stroke. For example, cross-hatching, which looks something like this, is characteristic of having an incorrect SIM vector in the reconstruction. So the bands aren't put together quite correctly, and you have this sort of cross-hatching or ringing effect. You can also get these honeycomb patterns, which can come, for example, from out of focus background light that is incorrectly mixed into your shifted bands. We'll discuss ways of mitigating this in the next section. And in general, I encourage you to check out this very nice paper from 2017 that provides a very complete understanding of what these various reconstruction artifacts indicate. In this next section, we'll discuss optical sectioning combined with SRSIM. Optical sectioning, in spite of SIM's close relationship to this technique and roots in this area, is typically not realized in the super resolution reconstruction algorithm, at least not in the Wiener filter one that we've just discussed. However, there are some easy ways to add optical sectioning, which can really improve the quality of your 2D SIM images. one of the reasons that there is no optical sectioning in this Wiener filter algorithm is the forward imaging model that we used assumes a 2D sample. So we ignored the possibility that there is out of focus light in this situation. And the problem with having out of focus objects is that we still see them in our sample, or to put this another way, the out of focus optical transfer functions still have significant weight at low frequencies. So if we look at this plot of optical transfer function, so the x-axis is frequency, the y-axis is magnitude of the transfer function, and these different curves are representing transfer functions for different defocuses. So 0 is no defocus. This is our typical optical transfer function. As we move an object out of the focal plane, we see less high frequency information, which corresponds to the object blurring. And for very far out of focus objects, we get very little high frequency information, but we see a big blur. We see, because our optical transfer function still has significant weight at DC. This is a big problem because this extra light undergoes our regular SIM demixing process the same way that the in-focus signal does. And that means that this out of focus light, which is predominantly at DC in our image, gets mixed into our higher order SIM bands, and therefore in the reconstruction algorithm, it gets shifted out to approximately the position of the SIM frequencies. And then we see it in our image, not only as an out of focus blur from the 0th band, but from the higher order bands, it can show up as sort of a hexagonal pattern or other artifact in the reconstruction. So one approach to get around this, which was, as far as I know, first suggested in these papers, is an approach called band replacement. And so what we do is we take our separated SIM bands, consider, for example, the unshifted band, the 0th band. Now we know that at DC, this band is corrupted by out of focus light, but this shifted band does not have any effect from the out of focus light at this same frequency position. So if we attenuate the signal in our unshifted band computationally and replace that with our shifted band, then we've got rid of a lot of this out of frequency light. And similarly, we should do this in the higher band, in the first band, but here at its shifted center. And so that's what these other plots illustrate. So in particular, if we look at G, this is showing us these red regions are the regions that we like to keep information from the 0th band, while the green regions are where we'd prefer to keep information from the shifted bands. And so we implemented this technique in our mcSIM approach. And I'll show you a small simulation we did to illustrate its effect. And then later in this presentation, I'll show you how effective this is on real data. So here we've simulated a pattern that consists of a pair of line pairs that are progressively further spaced apart, and a few microns above it, a fluorescent disk. If we naively apply our SIM reconstruction algorithm, you can see we do a decent job of reconstructing the line patterns, but we're corrupted by this out of focus light that exhibits various ringing artifacts and also sort of hammer stroke artifacts. And if we look at the Fourier transform of this image, we can easily see the regions where this disk is creating artifacts. So in particular, at DC, some of these concentric rings are coming from the disk pattern. And then at the SIM pattern frequencies, where the shifted bands have taken the erroneously mixed information from DC and shifted it, we again have strong artifacts here. It's less clear to see along this angle because of these FFT artifacts, but it's also there. And so now if we do the band replacement, you can see we're able to nearly completely get rid of that out of focus light in the SIM reconstruction. And effectively what we've done is attenuated this artifacts in the sample. In our mcSIM package, one way to look at this is to look at our reconstruction diagnostic, where we compare the wide field image and its Fourier transform with the SIM image. And so it can be convenient to compare these two in real space, and then also to look for potential artifacts in the Fourier space of the SIM reconstructed image. Although this technique is very effective, there is no free lunch here, in the sense that this out of focus light can still affect the quality of your SIM reconstruction because it decreases the MCNR. And particularly if you have a small amount of in-focus signal compared with the out-of-focus signal, this will pose serious problems to getting a quality reconstruction. So in particular, if we look at the MCNR, you can see in the region where the disk is, we have much lower MCNR than most of the rest of the image. This we could think about because this out-of-focus light, of course, adds to the shot noise in the image, but it doesn't vary with the SIM pattern. And so it increases the denominator of the MCNR without affecting the numerator. Now that we've discussed SIM and SIM reconstruction in detail, I'll show you some examples of the type of reconstruction that we can achieve with our package. And I really encourage you to check out part 2 of our tutorial, where we'll show you, using some of the same data, how to do these reconstructions. First, I'm showing reconstructions we did of a test target made by ArgoLight, this Argo SIM target slide, that consists of a series of line pairs with progressively smaller and smaller spacing. If you look at these in wide field, here we're looking at lines that are separated by 90 nanometers, 120, 150, and so on and so forth. We're unable to resolve the separation in wide field, but once we perform SIM, we can nicely resolve about down to the line pair that's separated by 120 nanometers, which is on the order of the expected SIM resolution for this particular, for our particular instrument. We've also performed SIM on fixed BPAE cells. Here we're looking at F-actin and cyan and mitochondria in yellow. You can see the SIM compared with the wide field, we get a nice boost in resolution. In this data set, we did not use the optical sectioning mode in the reconstruction. This was taken before we implemented that. And so you can see some artifacts out here, presumably coming from the out of focus light in this sample. As I mentioned, SIM is perhaps a super resolution technique that's most compatible with live cell imaging. Here's an example of some live cell SIM that we did, again, without the additional optical sectioning, looking at adenocarcinoma cells. And here we studied mitochondria in blue, vacuoles in pink, and F-actin again in yellow. More recently, we've looked at fixed samples of the cilia tetrahymena, which is a single cellular organism covered in cilia that it uses to swim in a variety of interesting strokes. And here we've studied the basal bodies, which are the sites where the cilia attach to the tetrahymena. You can see with our SIM, we get a nice resolution boost compared to wide field, as well as getting nice optical sectioning using this technique that we've just discussed. If we step through the Z-stack, you can see the wide field image on the left is heavily corrupted by out of focus light, whereas the SIM image on the right exhibits very little out of focus background. So the optical sectioning is very effective. You can more clearly see this if we look at the mcSIM projections. And finally, another view of this, we've rendered these tetrahymena in 3D, so you can nicely see their structure. The optical sectioning provides a very nice enhancement of the image. And we've tried running these through the recent sparse deconvolution SIM algorithm, which produces very nice results. These previous examples were all samples that we imaged on our home-built DMD SIM microscope. We've recently also tested our package on data from a commercial Nikon instrument. And so, as you can see in this 3-color sample, we're able to nicely enhance the resolution with our 2D SIM processing, as well as produce some very nice optical sectioning. We can also look at the Nikon reconstruction. So here they've compared doing 2D SIM and 3D SIM on the same sample. You can see the Nikon 2D SIM reconstruction also does a good job. But they don't implement this band replacement optical sectioning technique. And so if this is a feature that is important for your data, it can be useful to use our reconstruction approach. And you can see, obviously, we don't achieve the same resolution as the 3D SIM, but the optical sectioning does a very good job of removing some of this out of focus light, which is one of the big advantages of 3D SIM. I just will briefly introduce some of the other tools that our mcSIM package gives you access to. So we originally wrote this code with the intent of creating a package to simulate and control a homemade DMD SIM instrument. And so one big aspect of this was designing simulation tools to understand the complex diffraction model of a DMD, particularly in multicolor settings. So we've developed a variety of tools to do this that helped us design our system. Recent talk by our group at Focus on Microscopy showed a variety of interesting multicolor solutions with a suite of available DMDs from Texas Instruments. So if you're interested, I encourage you to check that out and check our code out. And then finally, we have a full experimental control code available as part of this package, running based around micromanager at its core, in particular the micromanager core C++ code, but recently we've transitioned to using a Napari-based GUI, PyMM Core Plus, to control our instrument and ultimately reconstruct our SIM data using the code and the procedures we've discussed so far. So if that's something you're interested in, I encourage you to check that out. And so with that, I'd like to acknowledge everyone in the Shepherd group who's been involved in this project, as well as some of our collaborators. please check out our package on GitHub, or if you're interested in our DMD sim work, you could check out this paper from last year. I'll encourage you to check out part 2 of this tutorial, which is a coding tutorial that Doug is giving. And also, please stay tuned. We are working hard on a Napari plugin to simplify the use of mcSIM even further. So that'll be coming in the near future. Thanks a lot for your time.
Hello, my name is Doug Shepard, and welcome to part 2 of our multicolor STEM reconstruction workshop. In part 1, Peter Brown went over some of the theory and parameters that are important for 2D STEM reconstruction. And what I'm going to do now is go over 4 Jupyter notebooks that go through an important calibration that we do for our instrumentation that may or may not be present for yours. Then going over how you can sort of quantify sim resolution dealing with this Wiener parameter that Peter discussed. Then I'll go over a notebook dealing with optical sectioning strength. And so this will be a 3D data set, but it's not 3D sim, it's 2D sim and Z-stacks. And then finally, I'll show how to parse and load data from a commercial instrument, in this case, a Nikon. So to begin with, you'll need to navigate to our group GitHub page, which is github.com/QI2lab. And so that can be found here. And then you are going to go down to the repository for the I2K 2022 Sim Workshop. So this should be one of the first repositories, and we'll probably pin it to make sure that you can find it. So if you click here, there is a set of instructions on what you need to do to run the tutorial. So to do this, hopefully you're familiar with Miniconda or Python virtual environments you can use as well. In our case, we're going to use Conda to create a sim environment that we're going to call mcSIM I2K. And then we're going to use Python 3.9. You can, in an Anaconda prompt, so if I bring up an Anaconda prompt here, I could just copy paste this code. So if I copied this, and then I pasted it, it would show up and I would be able to run that. I've already created the environment, so I'm not going to do that in this case, but all of this should work. Once you've created it, that will take a few minutes. You may have to accept the command prompt. You need to activate that environment. And then inside of that environment, you're going to copy and paste this command about what to install. And so what we're going to install is our packages from GitHub, Napari, a tool to take line cuts in Napari, a tool for interactive plotting in Matplotlib, and then a tool to load Nikon ND2 files. Once you've done that, you then need to somehow clone this repository that contains the Jupyter notebooks. There are 2 options. If you have Git installed and you're comfortable with it, you can navigate to a directory and clone directly through the internet. If you're not comfortable with Git, you can go up to the top here, and then there is a code button here. I guess I've zoomed out so far, it's a bit difficult to find it. So there's an option, let me change the zoom level here. There it is. So this code button right here is what should allow you to then, if you click on this, download the repository as a zip file, and then you would unzip that file in your computer where you'd like to have the demo. And finally, we've provided 3 data sets and also calibration files from our experiments. And so you can download this example data archive. This is about 1.6 gigabytes. And so then you can unzip this in the data directory where you clone the repository. And so what the directory structure should look like once you have this is, if I look at this as my directory, what I have here is I have the files that were downloaded from GitHub. And then inside the archive file that we provide to download, there's this data folder, and I should just be able to unzip that and I directly get this. And then in each side of one of these, should be a calibration and a raw data folder. Except for example 4, there should only be a raw data folder. You can see I have some reconstruction folders here. You're going to generate those as part of the workshop. So once this is all set up and ready to go, then you're ready to dive into our examples. The examples, again, are listed on the GitHub so that you have a good idea of what we're going to be working on. And I just want to be very clear that, example 1 and 2 are samples that are in my lab using a ArgoLite sim slide. Example 3 is using an immunofluorescence labeled tetrahymena that was prepared by Nick Galati at Western Washington University. And example 4 is using COS cells that are immunolabeled for 3 different proteins, and that's generated by Christophe Lettier at the Neurocyto lab. And so he very generously both generated the samples and took the data on the Nikon instrument. Okay, so let's get started with the examples that we're going to work on. So I am going to use VS Code to do this. If you prefer to use Jupyter Lab or whatever you want to do to load the Jupyter notebook, you can do that. And then in VS Code, once I open one of these notebooks, and so if I look at the Explorer, how I would do that would just be to click on the notebook and bring it open. I've already opened all 4 here. The important thing to make sure is that you select your Python environment correctly. And so you can see up here, I've selected mcSIM I2K, and it tells me it's a Python 3.9 environment. So in this first notebook, what we're going to look at is a calibration process we do that we think helps a lot with 2D sim. In fact, it would help with any structured illumination method, is that we estimate a transformation from our spatial light modulator to the camera. And so how do we do this? We put on a grid pattern of dots. We then display that pattern into a uniform thin slide of dye. And so in this case, we're going to use FITSI. For one channel, I think something red in the other channel. It's not Texas red. It's like a sort of dye that comes from one of these older papers, and then Alexa 647 for the red channel. And again, in our case, we use a digital micromirror device instead of a liquid crystal on silicon spatial light modulator. But as long as you can control the modulator, it doesn't matter. You could do this. So there's a bit of a description in the notebook that tells you exactly what it's going through here. I'm not going to read that to you. I'm assuming that wouldn't be very interesting. What we do have is then hopefully enough comments in all these notebooks that you can kind of figure out what's going on. So each of the notebooks starts with library imports. And so, there are standard libraries that we require, such as NumPy, and then we use pathlib to manage file names. We use matplotlib to display plots if we're not going to use Napari. And then from our own package, we import a number of tools. And so for this particular example, we're going to import a module that performs the fitting from the DMD to the camera, and then a module that allows us to generate sim patterns. And so you can see for each of these, I can pull this up and I have doc strings. This MMIO module is specifically a module that allows us to load Micromanager TIFF files. For those of you who dealt with this before, they have a slightly different structure than a standard OME TIFF. So then for all of these notebooks, we're going to have to both define the file names and the metadata. We do store this on disk from our instrument, where I'm going to explicitly define it in these notebooks just so that we have everything really laid out so you can see everything that we're doing. And so here, we're going to load a TIFF file that contains these images of the different patterns. I know the order of the experiment was our 465 nanometer laser, 635 and 532. The reason this is 465 has to do with when we actually tested the wavelength of the laser we bought, it wasn't the 471 as quoted. And so we actually then went ahead and fit it and figured out what the center wavelength actually is. Then I'm going to provide some metadata to the fitting program, and what these are where I think the center of the pattern is on the camera chip. So the camera chip is 2048 by 2048. These are roughly the Y-X centers of the pattern for each channel. So again, channel 1, channel 2, channel 3. And then these have to do with the indices on the DMD. And so these are specific to our experimental hardware. And if you're going to do it for your own, you need to work out this a little bit more carefully. There's details in the code. I'm then going to set a region of interest size around each of these dots that I display on the DMD. And so how do we do that? We just turn a set of mirrors on that I want to fit. So I'm going to call that 25 pixels. I then know some metadata about the experiment. So I know our camera pixels are 6.5 microns, our DMD pixels are 7.5 microns. And then we, from physical optics, know what the rough magnification we expect between the DMD and the camera is. And this is just based on the relay lenses and the tube lenses. So for example, we use an Olympus tube lens, so that's where this 180 comes from. These two lenses are the images that form the relay train, and then the 200 millimeter lens is the lens that collimates the light coming off the DMD. Then we just have a simple Gaussian fitting function that we're just going to use to allow us to do this in the magnified space. And again, I'll show you what the patterns look like in a second. From our DMD object, we're going to generate the patterns that it would use. And you see here, this actually would allow you to generate these patterns. So if you had a modulator device, as long as you know the size of the modulator, so in our case, it's 1920 by 1080, you can automatically generate these patterns to load, display, and then use for fitting. You don't have to generate these on your own. And then what we do is we just run a calibration for each file. And so, we load the data, and then we run this affine transform. And so again, hopefully you can see all of our functions have pretty intensive doc strings involved in them. And so everything should be defined pretty well. So the result of this is we get the following outputs. And so what this tells us is it tells us here's our data in yellow, and then all of our fits in red. Do you see the fit points are the red X's, the affine transform is the yellow, and then the purple is where the DMD axes are. And you can see that is these two purple lines right here. And so what those are telling us is, the DMD is a bit of a unique spatial light modulator, and it doesn't actually sit sort of level with the table, and the mirrors are actually slightly tilted, and so we have to figure that out. So what this then allows us to do is then fit exactly what the mapping is for, say, our first laser would be this output. Here's what the actual pattern that was displayed on the DMD is. And then here's the second laser output. You can see actually some junk in the dye slide here, right in this spot right here. And then here's our third output. And so you can see here, actually the beam is a little bit bigger, so we have a bit of overfilling going on. So the reason we go through this is that what this allows us to do is to have an exact knowledge when we put a pattern on the DMD, what we should expect to see on the camera. This is really valuable because then we don't have to go through and manually calibrate where the peaks for the SIM pattern should be. It also allows us to exactly know what phase of a given pattern we've applied. So this removes a lot of the guesswork. That said, I will show you in the last example, if you don't have this information, how to use Fourier transforms to then get at least a start to that, and then use diagnostic output from our package to make sure you've got everything correct. So you can run through these on your own. Again, all the data is provided. So in example 2, we're going to use this Argo-like SIM test target. And so they now have a version 2. We own the version 1. And so I've provided a link here to the version 1 PDF. And so if we click on this, then what we can see is this is a test slide on page 12. There's an overview of all the different targets that are on the slide. And then if I go to page 21, you can see we can actually see the targets that we're going to use. And so the targets are lines that are sort of racetracks. And then the inner part of the racetrack, which is here, has a spacing. That spacing varies from 390 nanometers to 0 nanometers in 30 nanometer increments. And so one can use this as a test target of how well your SIM is doing. The other reason we really like this set of test targets is that they change angles. And because in SIM, we rely on 3 angle patterns for 2D SIM, this is a really good test about whether or not you have a bias in one of your angles. So if something's happening where you're not maintaining your polarization correctly or your modulation depth correctly, this will tell you that, because you will get different results from the different angle targets. For the purposes of this example, we're just going to load one of the test targets. If you look at the paper that Peter cited that we published on this instrument in this package, you can see that we provide data from all of them. So again, we have a number of imports here. We have more this time. And I do want to say we do store our fine transformations and our patterns as NumPy pickle files. And so if you're uncomfortable loading these, that's fine. Please reach out on the GitHub issues, and what we can do is resave those as a ZAR for you and then upload them and give a slightly modified version of the code. This is just how we had originally started doing it for our fine transformations, because we're not typically sharing that information outside of the instrument. So then what we're going to do again is explicitly write the metadata down instead of dealing with automatically loading it from the instrument, just so that we get a real sense of what's happening here. So I'm going to define the number of colors or channels as 2. We're going to use the 465 and the 532 laser. I'm going to say that we have 3 angles and 3 phases of our SIM patterns. This is required for 2D SIM with a sinusoid pattern. We only have 1 Z-plane. We just took an image where it's in focus. We then have 2048 pixels, both in X and Y on the camera. And then we're going to read the data from the disk. We've already predefined this, assuming, again, that you use the directory structure that I pointed out you should have when you load this. So again, your directory should look like this, where the top level of your directory contains the files from GitHub, and then you decompress the zip file into here. So what we can do is then we can just load the raw data in Apari. And so I've written a set of lines here that allow you to launch Apari from a Jupyter notebook, correctly set the scale, put some color maps in there, and then make sure that we can actually have sliders that correspond to our angles and phases. So I'm going to launch this, and then I'll bring the window over here, and I'll zoom in, and we'll change our color map. And actually, we're just going to look at the blue laser because it's a bit brighter. So what we have here is that test target. You can see I'm only showing you one of the ways. And if I zoom in, you don't see very much modulation due to the pattern at this angle. So the sliders down here on the bottom, we have both the angle and the phase slider. So if I change the angle, now all of a sudden the angle of the pattern has changed relative to the structure in the test target. You can see we have a very different modulation pattern. And as I change the phase, you can see that that modulation pattern moves. And so this actually is what the raw SIM data should look like. If I look here, you can see there's a hint of that. But because the pattern is much closer aligned with the angle of the lines, it's actually not modulating nearly as much. And if we go to the third angle, you can see now we have a yet different, again, modulation pattern that changes with the phase. And so this is really important in raw SIM data, that you actually can detect these if you're working at SIM frequencies that are, inside the detectable limit of the system. Turf SIM or other methods have exceptions to this rule, and they require special care. Those are not really data sets that our package is suitable for reconstructing at the moment, without a lot of sort of guesswork, because we're not really using that modality. All right, so I'm going to exit out of this Apari window. And then what I'm going to do is I'm going to crop the raw image so that we're just going to reconstruct the area that contains our structure of interest. Otherwise, we're just going to be performing SIM on blank areas where there's no interesting information. We have a function to help with doing this, where if you hand it the corners inside the image space in pixels, it will then give you the centered region of interest around that. And then what we can just ask is, how wide is that in X and how wide is that in Y? So that's what this block is doing. Then what we're going to do is, from the disk, we're going to load a lot of calibration data about our instrument. And again, we're going to specifically use that because we have it. In the last example, I'll show you what to do when you don't have it. So we actually characterize our optical transfer function using a method that directly maps in frequency space instead of inverting a point spread function. And so we have that data saved to disk. We provide it as, again, this pickle file. And so this loads that, and then we provide a quick function here to help calculate what that frequency response should look like of the system. We then know our pre-calculated affine transforms for the current alignment of the system when we took this data. So you can see this was from last year, roughly a year ago, 14 months ago. So we load that into disk. And then what we do is we use the optical transfer function and the affine transforms to transform the DMD, the patterns we displayed on the DMD for this experiment, and actually get what the frequency of the pattern, the sinusoid pattern, should be. And then we get what the phases are out of this. So to do that, we load the DMD patterns from the disk. What we then do is loop over all of the channels, and we figure out, using the affine transformation, what frequencies we think there should be and what phases we think there should be. We then create a grid where the grid contains the spatial frequencies of the system in the correct units. And so this is something you always have to be really careful about when you go from spatial real space to spatial frequency space, that you use the correct units. And then what we do is we use a part of our affine package to actually to do the affine transformations, so that we can then go through, and again, the doc strings here are fairly intensive, of take our patterns and then transform them into what the actual frequency and phase should be. I'm not going to go through all of this because not every instrument has this. What I just do want to say is that this has, a really useful thing in that we know exactly what the sim pattern should look like. So before I move on to trying to run reconstruction, I can quickly make a comment about, why is this calibration important? So at the very bottom of the notebook, I have a piece of code, which is how you would try and find where the frequency peaks are if you did not have this calibration. And so what you do is you take the Fourier transform of the data, you then place it on that grid I was talking about with the correct spatial frequencies, and then you plot it. And then this is what it looks like. So this, because these are line structures and they have high frequency structure, you can see it's a bit confusing here if I zoom in to try and understand, like, what is my sim peak in this case? Like, which one of these things actually corresponds to my sim peak? And so this can be a pretty tricky situation to figure out when you have data that looks like this, or if you have low signal to noise data. And so again, this is why we think having these calibrations is really important. And so it is possible to do it from this data and a bit of prior knowledge about where you think the peaks are. But in this type of, sparse structured data, this is what the Fourier transform looks like. And again, it's not obvious, which one of these high frequency peaks should I be picking for the pattern. If I then look at another angle that was displayed, you can see actually my Fourier transform is different now, and I have more information contained along one of the other angles. And so likely one of my sim peaks is out on these other pieces out here. So this removes the guesswork is what it comes down to, but it is not, absolutely necessary. You can manually calibrate this on your own. And again, we'll look at that with some real data at the end. That's a bit easier to deal with in this test target. Okay, the last thing I want to do on this example before we look at the sim reconstruction is show you that the doc string for the sim reconstruction class actually has quite a lot of information contained in it. So there's a bit of text about, how you should use this. You need to write some helper functions if you don't want to loop over, say, Z slices. That's what these notebooks are doing for you. But also each parameter is pretty well described. So example, the first parameter is the physical parameters of the system. So this is the effective pixel size of the camera, the numerical aperture of the objective, and the emission wavelength we're working at. Then you have to hand it the angles. It tells you the order it wants it in if you're creating your own data. So you need to have angles, phases, Y, and X. And again, if you want to do Z, you just need to loop over all of this. If you don't have your optical transfer function like we do, and you put in none, it will actually use a theoretical model to investigate this, or to generate that from the numerical aperture. We've also been working with groups that have systems where you have slightly different optical transfer functions per acquisition angle due to the complexities of the instrumentation. So actually we can ingest an optical transfer function per sim angle in this case. And then the last sort of piece I want to point out here is this Wiener parameter, which is something that Peter showed you in depth about how this sort of affects how much we suppress these high frequency noise features, potentially at the cost of super resolution information. And so what we're going to do for the rest of this example is actually look at what changing that Wiener parameter looks like for the test target. So I'm going to go ahead and collapse this detailed information from the sim reconstruction class. What that is just the doc string that I've copied out so you have access to it. So then what we're going to do is I've defined a set of Wiener parameters that we are going to run over. And so I've done this in this code I've highlighted here. So we're going to try 0.05, 0.1, 1.15. So increments of 0.05 from 0.05 to 0.4. If you use 0, this won't work. And so you need to have at least a small finite value for the Wiener parameter for our reconstruction to work. I'm then going to loop over all of those parameters and then perform sim reconstruction. So what I do is create the object, feed it all of the parameters that are required. And again, I've expanded the doc string for you in this cell above. Then I'm going to call the reconstruct function. I'm going to tell it I want it to plot the figures, I want it to save the images, and I want it to close the log file. I'm then going to grab out of the object the wide field and the super resolution image for display in Napari afterwards. So I've already pre-calculated this, so we don't need to wait. You can see on my laptop, which is a Microsoft Surface Pro, it took about 5 minutes. And so, your own experience may vary depending on the type of computer you're trying to use. I've hidden the output from the code. If I expand this, you can see it's actually outputting a large amount of diagnostic information. And again, we're going to look at that in a later example to understand what happens when that fails. But for now, I'm going to go ahead and hide that again. So let's look at the results in Napari. So what we have here is on the channels, I've put the super resolution in orange, and I've put the wide field in blue. And so if we zoom in, let's say on the 390 nanometer line, and I turn off the super res, here you can see the wide field in blue, still very nicely resolved. And if we then grab the super resolution image, we can see we have a much better resolution of those lines. So now what I want to do is I'm going to slide the Wiener parameter. So here is where the Wiener parameter is the smallest, which remember again is 0.05. And so now you can see as I start to slide over, what starts to happen is the images both get dimmer and we start to lose that high frequency noise. And so it can be useful to look at the edges of these resolution targets. And then here you can actually see one of these classic artifacts, the hammer stroke artifact that Peter referred to. So as I bring the Wiener parameter up off the floor, you can see right around here in the middle, which would correspond to, let's see, 0.05, 0.1, 0.15, 0.2. Now we've suppressed the high frequency ringing artifacts, but we've still retained a fair amount of the super resolution information. And in fact, you can see as we go down and down, here I can't tell the lines apart in the wide field anymore, say after about this line, but I continue to see the line separation almost all the way down to this one. And so if we count the line spacings there, 390, 360, 330, 300, 270, 240, 230, 210, 180-ish. And I would say conservatively, maybe we could go to 150. We would have to take some line cuts and fit. And so this Wiener parameter really controls that. So what happens as I start to go even further? You say, oh, well, the image cleans up even better. That's true, but you can see we're really losing signal. And the reason we're losing signal is we're suppressing that high frequency information more and more, which means we're losing that when we recombine the super resolution information, we're not putting as much information back into the final image. And so actually we have almost worse information, worse reconstruction in this case. And so if we look at these two line pairs, as I bring this back up and I adjust the contrast to account for it, you can actually see there's a little bit more information in the super resolution reconstruction with a lower Wiener parameter. And so how Peter suggested to diagnose this, looking at hammer stroke and looking at the Fourier transforms, is the correct way. But I just wanted to give us an example of what that would look like here. And so again, you can run this on your own and play with it. You could try other Wiener parameters. You could go all the way out to 1 and see what it does. And so this is a really nice sort of test about what the reconstruction algorithm is actually doing. One thing I want to add to this is that all I've plotted for you here is the output. But if you go into the data structure and we go into example 2, in the reconstruction directory, there's actually a huge amount of diagnostic plots that mcSIM generates. And so one of the most important ones when we're talking about picking this Wiener filter is this set of PNGs that's generated for the SIM reconstruction. And so let me just grab this one and bring it over. And so let's see. It's got transparency on, so I'm worried it's going to be difficult to see. Fortunately, I think we'll just have to look at it this way. And so here, what you can see is, I'll read these off to you: the wide field, the Wiener deconvolved image, the SIM image, and the optical sectioning SIM image, which just follows the classic law of sines reconstruction. Here's the original image with these red dashed lines correspond to the numerical aperture of the instrument, and then 2 times the numerical aperture. Here's the Fourier padded image where now we can fill in that space with the extra information with the SIM. And then here's the final Fourier transform. And these edges really are what we were referring to, like how noisy are these edges? And so if we go to 0, we can start to see it's sort of sharper there than at the lowest Wiener parameter than versus say one of the higher ones, which is if I click over. And so this roll off is really what starts to contain that information. And so I just encourage you to go through the directory and take a look at what is in all of these. And so all of the theory that Peter presented, there is a plot for each of these that's associated with that, in addition to the raw data, which is saved as TIFFs with the metadata written into them. So for each reconstruction you'll get one of these. And then you can see here, I've just put the index of the Wiener parameter. So you'll actually have to correspond this back to what are the arrays held. So for example, W000 is the 0.05 Wiener parameter. Okay. So this is our first exploration of what parameters are important for, doing SIM on thin samples where there's no real out of background light. The other thing that Peter discussed in the theory section was that we can also include optical sectioning by doing band replacement. And so here, this is really helpful when we look at a biological sample that may have fluorescence above or below the focal plane. And then if we're going to try and perform either a Z-stack, or if we just need to try and limit the amount of corrupting fluorescence in that around that DC frequency, then what we can do is we can also add optical sectioning into the super resolution reconstruction. And so what we've built into mcSIM is a variant on the existing methods published by Shaw and O'Halloran. And so those references are both in the code docstring. And so if you come back to here, and then we look at the docstring. So in example 2, remember where I had pasted all the docstring information. If we come down to, where is, optical, for more details on the band sectioning and optical replacement approach, we have the 2 references here. So if we click on each of these, it will take you to, that's interesting. We will update the code to make sure that that works. I think it's because there's a slash there. So I will make sure that that's fixed before you download these. But these are the 2 references. And we'll make sure that the hyperlinks are working. Okay, so again, those are by Shaw and Halloran, and we just introduced a variant on that. So again, we're going to import our libraries. There's a number of analysis tools that we bring. This localized PSF is also our library. We use this for various sort of fitting functions. And, the rest of this should be very similar to the previous example. Again, I'm going to explicitly define the experimental metadata here. Normally, we would load this from the metadata on the disk using a slightly different function, but I just want to make sure that we're all on the same page. So we're only going to look at one channel of this 3-color experiment. We're going to look at 3 angles and 3 phases. There are 35 Z-planes spaced 250 nanometers apart. Same camera, so 2048 pixels in X and Y. And then we just read in the data from the disk. Here's our experimental metadata. So, our NA is the same, 1.3. Our pixel size, effective pixel size at the camera, 65 nanometers. The DZ step with the piezo stepper is 250 nanometers. Here's our excitation and emission wavelengths. So let's look at the raw data, just like we did with the other bit. And let's see what the error was here. Oh, I just had there we go. So I was using NumPy squeeze to get rid of singleton dimensions, and I just had a syntax error. Okay, so here's what the raw late data looks like. Again, these are basal bodies in tetrahymena. So let me bring up the contrast here. And you can see we have this one area that has a lot of background fluorescence. And so if we look at this in 3D, well, we can see if we rotate that over, and so you can see there's actually another tetrahymena that's sort of in the corner over there of our region of our camera, is, we have a pretty large amount of background fluorescence that's coming out of this object. And so this is going to be a good test for us about how can we try and limit the deleterious effects of that on our SIM reconstruction. You can also see we just have a fair amount of background haze from the fact that this is a 3D sample. So let's zoom in here on one of these basal bodies, maybe try and get it in focus. So that looks like it's about the focal plane. Now what I'm going to do is I'm going to step the phase, and then I'll step the angle. And it's a bit much harder to tell in this case what's going on. If I change the contrast back to where we can see information in this very bright set of immunolabeling, here you can see now I'm changing the angle, and then I'm changing the phase. And so you can see we've got this sort of correct action going on. Okay, so what we're going to do is, again, cut out that other tetrahymena that was in the window. And so I'm just going to define this region of interest. If you needed to do this on your own, what you could do is just load Nepari or load the data in Fiji, find the box, find the two corners that correspond to it. You would then put those in pixels here in YX order, and that's where this notation's for. And this will give you the region of interest. And then the reconstruction software will automatically take that region of interest. You don't have to define the coordinates anymore. We're going to do the same, loading the transfer function, loading the affine transformation, and estimating the patterns that we did before. So all that remains exactly the same. This is the exact same code as the previous example. And actually, normally we hide this behind in the reconstruction object, but I really wanted to step through everything so that you can see what's going on here. And then now we're going to perform the sim reconstruction. So here, instead of stepping over the Wiener parameter, what I'm going to do is I'm going to step over the amount of band replacement that we perform as a percentage of the maximum sim frequency. And so what I'm going to do is I'm going to use values of 10%, 20%, 30%, 40%, and 50%. And these have to do with essentially where we center, where we start rolling off the zeroth order band into the band from the sim to replace it. And so Peter's got a nice set of slides about the theory behind this in the part 1, and so I encourage you to go back and take a look at that. The rest of this gets set up exactly the same. It's just that in this case, I'm gonna loop over this band exclusion, and I'm gonna do the same thing again. Create the object, run the reconstruction, run the plots, close it. I'm gonna grab the data to save for display in Nepari. I chose to pre-generate this for the entire Z-stack on my laptop. If you're doing this on your own computer, you may want to change these parameters to just reconstruct a couple Z-planes to play with. And so, if you want it to look where there's really nice data, things like maybe planes 9 to 12 is a great place to start. If you do choose to run this on all of it and you're using kind of a standard laptop and not using the GPU, be warned, this cell took about an hour and 25 minutes to run on my laptop. And so it's doing a lot of data because it's not just doing the Z-stack, it's doing the Z-stack for multiple parameters. And so we're generating a huge amount of data in this case. So once you've done all of that, we can take a look at what the effect is. And so if we open this up in Nepari, what we can see, and let me slide this band replacement all the way over, and let me bring the contrast up for both of our bits. And so if we just look at the wide field, this is the data we were looking at before. If we scroll in Z, you can see we see the basal bodies, no problem. We have this bright area. So now let's turn on the super resolution reconstruction. And actually, you can see due to the out of fluorescence light, we have a huge amount of hammer stroke if we don't perform any band replacement. And so here we have this really noisy sim reconstruction. And so this is a really sort of classic problem you can run into with sim. So how do we attempt to suppress that DC information from making it into the sim reconstruction? Well, we can turn up the band replacement. So you can see as I turn the band replacement factor up more and more, I start to limit the deleterious effects of that reconstruction. And then what we can do is we can just look at what happens if we bring the noise floor up just a little bit. And we can then render this in 3D. What you can see is there's still some noise. But overall, what we've now accomplished, if we bring the rendering so it's not so bad, is now we actually have a pretty nice sim reconstruction in 3D, where we've really limited the effect of the out of fluorescence light. We haven't optimized the Wiener parameter here at all. I just took a guess at what it should be. And I also haven't optimized what I think the background is. And so again, let's just turn on the wide field in this case. So here you can see you've got this kind of background haze, and you also have, if I zoom in, sort of this classic diffraction limited spot. If I then turn on the sim reconstruction, you can see we still have a little bit of noise going on. So if we, clip the background just a little bit for the purposes of display in 3D, you can see the parameter guesses we had are starting to really narrow up some of these puncta in 3D. And so with a bit more optimization, you would be able to get to the reconstruction quality that Peter showed in the talk, because this is the exact same data set that he showed. And again, there's no other subtraction going on. What he did, he just spent more time optimizing the parameters than I did, because he's running it on a large computer, whereas I'm just running this on my laptop. And so, this is the start of why this optical sectioning inclusion is so strong, is that now, right, if we just look at the SIM data, you can see we've pretty much eliminated almost all of the background blur that we had by using the information in the SIM bands to get rid of the information near the DC peak. So again, just to click this back on, lots of background haze, really large amount of background light in this area with a lot of labeling. Whereas now when I click here, actually we even start to try and recover some sort of super resolution, or even maybe just normal diffraction limited resolution, but limiting that out of background light there. So we really think this optical sectioning method that was introduced by Sean O'Halloran is incredibly powerful. And this is one nice feature that's included in our software that a lot of the commercial reconstruction softwares don't include. So if you want it, again, to get the best reconstruction possible, one thing you could do is open a GitHub issue and ask Peter for the parameters that he used for this. The other thing you could do is just, iterate over a few Z-planes of checking both the band exclusion parameter and the Wiener parameter to try that. And I'll leave that as an exercise for you to work on. At the very bottom of this notebook, I've again generated the FFTs just to give you an idea of how it can be tricky to find these peaks in this sparse data where you have background. And so I'm not going to go through these. Again, it's the same code that we had in the previous block. I've just only generated it for the 9th Z-plane, and that labeling is, done, or that selection is done here, where I've said I just want it done for those planes. Okay. So we've looked at the calibration that we think is really important to be able to let us not have to manually pick the frequencies and the phases. We've looked at the effect of the Wiener parameter on the reconstruction quality for a thin object. We've looked at the effect of the optical sectioning for a thick object. And so the last thing that I want to do is I want to take a look at what can you do when you don't have the calibration data. And so here what we're going to do is we're going to use data taken on a Nikon InSim in 2D sim mode. And so these are going to be cost cells that are immunofluorescence labeled for microtubules, clathrin, and actin. Again, these are provided by Christophe Lettier from the Neurocyto lab. And so here we have a little bit different workflow. We're going to add an import into our imports, the InD2 print library. And then what we're going to do is the same as always, define our data path. But now I've written a large piece of data, and actually this can be wrapped as a function to return both the metadata and the raw data from an Nikon InSim storage. And this is a little different because it turns out the way they store the raw data is not the way one would naively expect it would be stored. And so I'm not going to go through the full details of this code. What I am going to do is show you the consequence of how they store their raw data. So this uses the ND2 package to pull all the metadata out automatically and pull the data out automatically. So you don't have to define wavelengths, pixel sizes, numerical aperture, any of those things. It's all grabbed from the metadata. The reason this is important is that the way that Nikon saves the raw data is very different from the way that we save the raw data. So here's what the raw data looks like from Nikon. So they create one large image that contains all 3 angles and phases per channel. So you can see I've created a raw slider here for the channel. And as I change this, you can see our different laser wavelengths. And all of the information for each channel and angle is contained in this large image. So that code block that I provided at the beginning of this notebook, what it does is splits these into individual images that are in the correct order for our reconstruction package. And so that can be wrapped as a function. And if you are interested in running this on Nikon data more, I've already provided a Python file with a command line interface through to a collaborator that you can then use to just load your Nikon data and iterate through everything. And so I'm happy to provide that to anybody. You just open an issue on the GitHub and we'll just add it to it. I just don't want to clutter this workshop. So if we get rid of this raw data, what we can see is after that code is run, what we now have is the correctly parsed data that we need. And what do I mean by that? So we have angles and we have phases, and then we have channels that are all separated. And so now we have the data in a NumPy structure that's appropriate for us to now try and use the mcSIM package to do the reconstruction. So again, this, you shouldn't have to do this on your own. If you have data from another instrument, say Zeiss or another SIM instrument, OMX, we're happy to work with you to write a wrapper so that you can get it into the format that you need to read this correctly. Okay, so now we can't skip the calibrating it ourselves step. And so I'm going to use that same code that I showed you in the previous code blocks, where we grab the data, calculate the correct spatial frequencies for each wavelength, and then plot the Fourier transform. But now we actually need to use it. We can't skip it anymore. So what we're going to do is we're going to look at this here. And this is the reason we want the matplotlib interactive window. So now when I zoom in here, hopefully this works. I'm going to rerun this real quick so that we get the correct interactivity. So if I zoom in, let me reset it. Okay. So if I zoom in on this peak, here's the peak that corresponds to the frequency of the sinusoid. And so we can see that this peak is at -3.2 in X and -0.9 in Y. So what we're going to want to do is actually record that piece of information for angle 0 for channel 1. So how I'm going to do that is I'm actually just going to minimize this block. And then in the next block, I have a set of variables where I've defined for each channel, for channel 0, 1, and 2, I'm going to append the frequencies that I find. So you can see I've already done that here. So -3.3, -0.92. And so now I will go back through and I will do this for each one of these, right? It is possible to run an automatic peak finding routine. The problem is if you have data all the way out near the peak, or the peak for some reason is low signal to noise, that can fail. And so we find this is a much more reliable way to get a guess. And then what we do is optimize based on that guess. So you can see this first one, or for angle 1 is roughly -2.4, 2.4. And so if we go down to the code block where I'm defining everything, you can see I'm in -2.4, 2.4. So again, this is what you have to do if you don't have the initial data for the calibration, is you have to go through each of these for each channel and each angle and define all of these. The reason you have to do it differently for each channel is that because the wavelength of light changes, you can potentially end up with a SIM peak in a slightly different frequency. And so what we can look at here is if we look at the actual ones that I find, you can see they do shift based on the wavelength. And so you can see that actually, they're close. They're roughly in similar areas in frequency space, but they're not quite in the same spot across the wavelengths. And so if we're not close enough to start, then optimizing based on that will fail. And so again, plot the Fourier transforms, zoom in on the peaks, grab the number, and then you would write them into this array here. And again, the order here is channel 0, channel 1, channel 2. And I've already done it correctly, and so you should be able to kind of parse how those things are working from there. Now that we have the patterns, we have to deal with the phases. Here we have less prior information, and so what we're going to have to rely on is the fact that for 2D SIM patterns, the phases should be relatively phase step 2 pi over 3 radians or 120 degrees apart. However, the order is not really well known. And so what I have here in the block that I've already written is the correct order for the Nikon instrument, but I arrived at this by trial and error. And so for different instruments, this may be different. For normal sinusoidal SIM node, it should be 120 degrees, should be the pattern design, which is when you add them all together, those three should give you uniform coverage, which is why that's chosen. So we have our correct phases that we've used as our guesses from our Fourier transforms, but we're not entirely sure. Sorry, we have our correct frequencies, but we're not entirely sure about the phases. What we can do now is use the diagnostic output of the mcSIM package to optimize what order those phases should be in. So before we do that, we need to define the reconstruction parameters that don't have to do with the frequencies and phases for this situation. So those are going to be the Wiener parameter per channel, the band exclusion fraction per channel, and the image background per channel. I know from optimizing ahead of time using the same strategy of looping over images as the previous two notebooks that this Wiener parameter and band exclusion work pretty well across all of these channels. They can be further optimized on a per channel basis, particularly for this data we're looking at. One of the channels has more background out of focus fluorescence than the other channels. So in here, I have a second or an initial reconstruction notebook cell. And if we just quickly scroll down before I describe it, what we'll see is that I'm going to try and recombine the SIM images using incorrect guesses. And the reason I'm going to do this is so that we can see what the failure mode looks like. So what I've done is I've intentionally perturbed the frequency guesses for channel 0. And then I've also intentionally flipped the phase information so that it is not correct. And actually, it looks like here I haven't done that yet. And so what I'm going to do is I'm going to go ahead and just alter channel 0 so that it looks like it's the wrong order compared to what I know it is correct. So we're going to say, instead of going 0, 240, 120, it's going to go 0, 120, 240. And then I'm going to save this to a separate folder that says incorrect guess. And then also what I'm going to do is I'm only going to reconstruct that first channel. So instead of looping over all channels, I'm going to define a variable that just tells it to loop over just channel number 1. The rest of this is exactly the same as the previous examples. The only difference in terms of the way the code looks is because we now have all of the metadata for each of the channels defined from the Nikon ND2 file. Those are now held as variables within the Jupyter notebook. And so I'm just going to use these as arrays. And when I iterate over channels, I'm going to grab the numerical aperture, the pixels, effective pixel size, and the wavelength for those. I'm also going to extract the individual SIM images for angles phases that correspond to the given channel or z-index. The rest of this is exactly the same. So when we run this, what we're going to find is that the program will spin up as normal, and then it will report back some diagnostics that I was hiding on the previous notebooks because I had already run it. And so the first thing the program will do is will attempt to fit the frequencies. So it will cut out a region of interest where we centered around where we tell it the frequency guess is, and it will attempt to find a peak in that box. And what we can see here is that it couldn't find a peak with a high enough signal to noise ratio compared to the value that we told it of 0.8. These SIM peaks should be quite high frequency. So what this means is it's going to default to the guess, and that it's not actually calibrated to what the actual angle of the SIM pattern is. This most likely means the reconstruction will fail. You really shouldn't ever be seeing this error message if everything is set up correctly. You always should be able to find the peak if you've picked those numbers correctly. The second important piece of information the mcSIM will hand back is that the attempted optimization over the phases failed as well. And so what you'll see here is it'll say that the phase guess is more than the maximum allowed phase error, which we define. And in this case, I allowed it to be 30 degrees instead of normally the 10 that we use, or 15, because I want it to give it more latitude since we don't know the calibration. What it will output is the code will output what it thinks the fit differences between what you told it and what it found. So here it's saying that there's really no difference on the first one, but then the difference for the second angle, it found a 218 degree difference, and on the third one, it found a 320 degree difference. If we look at those, these are actually relatively close to 120, give or take an error. And so that says the relative phase step might be okay, but it's the order that we've told the code maybe that they're happening in is incorrect. Here we see something similar. There's not a 120 degree step between these two, but we can see here we're actually something more like, what is that? 120 would be 200. So it's actually more like 70. So what this is just telling you is that the order, it's the wrong order. It's fitting the wrong phases. And this comes again from two sources of error. If the peaks are not found correctly, the algorithm is starting from the wrong point. And then if the wrong phase guesses are given, it starts from the wrong point. And then because we're doing band replacement, the band replacement algorithm will actually throw an error if it can't find any band overlap. And that is actually what happens when you get these things so badly wrong that the information is not being correctly fit. So what we could do is we could go back and say, well, I think I have the frequency that's correct, but I think maybe I screwed the phase up. Maybe it should, permute this. So what I'm going to do is just permute the phases. And so I'll move the middle phase to the beginning, and we'll try again. Now, again, this is still going to fail because we don't have the frequency correct. So I'm just going to go ahead and run this once. Do I have a syntax error here? It looks like I do. Introduced. This is always the problem with coding on the fly. There are 2 brackets. No, there are 2 brackets there. That was correct. That was correct. That was correct. 2 brackets here. There we go. All right. So now it's going to run, and we'll look at the output again. And again, this initial part will fail, but we should get new information about the phases. And so what you have to do is iterate between trying to get the frequencies correct and the phases. Most importantly, you should start with correct locations of the peaks in frequency space. And if you can't get those right, then the whole, the rest of it's not going to work. So again, now you see we have phase errors again. We also have frequency peak errors, and it's going to crash, and we won't get a good reconstruction. There are times in which it will find enough information to attempt a reconstruction, and then what happens, the reconstruction should look very off, and you also should be able to tell from those diagnostic plots that things are not being recombined correctly. And so typically this will show up as striped noise or striped versions of the image, or just really weird, kind of very, very strange looking sim reconstructions that aren't the typical noise artifacts that we discussed in part 1. So I've already, as I mentioned, found the correct values for the Nikon instrument for the data we were given. And so what I'm going to do is just bring those into memory to make sure that I have these 2 correct. And then what we're going to do is we're going to come down here and look at how I set up the reconstruction here. So it's really no different. It's just this time, instead of using those incorrect phase guesses, I'm going to feed in these 2 arrays, phase per channel and frequencies per channel, that are correct. So because these are now correct, what I've done is I've already pre-generated the data, and then what we'll be able to do is stop and look at that in the party. And what we're going to do now is look at the results. So what we have is on each one of these, the channel. So let's just start by looking at the Clathrin channel. So let's turn up. That's the wide field data. This is the sim data. And let's change the color scheme here so that we've got some contrast between the 2 of them. So I don't know, we'll do blue and yellow. So you can see we have very good overlap agreement, a little bit of hammer stroke noise, but not very much. And so here's our diffraction limited image, and then here's our sim image. And so you can see we've got some nice improvement in the sort of resolution among these. Also importantly, you can see we recovered information in the nucleus. So if I click here, you can see we have these very bright areas that are denoted here. So if I bring this back on, actually we've recovered what appears to be, Clathrin pits that were masked by that signal. And so I'm going to turn this back to blue for the super resolution image, turn off the wide field, and then bring all of our super resolution images on, and then just bring the contrast down. So we've got our microtubules, maybe a little bit of gamma just for the display on the computer. And then we have actin. See, what you can see here is we've recovered a pretty nice image out of that, the 2D sim data that was provided from the Nikon instrument. And in particular, we've recovered data where there is this high background. And so if you remember at the very end of Peter's presentation, he showed the comparison between this image for 2D sim and 3D sim. So obviously 3D sim is going to perform significantly better because it limits the both the axial information in terms of the out of focus fluorescence, but also in terms of the resolution. So you improve the transfer function in Z. But if we look at just the wide field data here, you can see we have a pretty big increase in the amount of information that we've gained by using this band replacement. In particular, in this area here, we really don't have a lot of microtubule data. So if I just replace that channel, you can see we've actually started a little noisy, but we've actually started to recover information out of this area that really just looks like out of focus fluorescence. And so, and again, this is for data that we don't have the calibration set for. And so, again, I grabbed parameters that I knew were going to work pretty well for this data set automatically. But one thing you can do, always just try different linear parameters, try different band exclusion parameters, and see what the effect on the signal to noise of the reconstruction are there. And so this is, to us, this optical sectioning is a really nice thing to have included in these reconstruction packages. It's something I think that makes mcSIM worth testing for people outside of it. All right, so I think that was the last example that I wanted to show in this tutorial. And I think it's probably the most important one because it shows you how to take data from an instrument where you don't have the calibration and run through it. So what I'd like to encourage everyone to do is to download the code, to download the data we've provided, and then on our GitHub on the issues, which is just up on the top, if you do run into a problem after you've watched the 2 videos, and you might need to go hand in hand with both of them to figure out some parts of this is just post and we'll be super responsive. And then what we'll try and do is have things set before the GatherTown if people look at this before then, and then we'll be available on the GatherTown to troubleshoot installation, downloading it, and then again, if anybody has sort of issues with using a pickle file on their computer, then what we can do is provide that in an alternative framework. And I will talk with Peter about getting that data set and done such that it can be loaded correctly. So thank you very much for watching both videos. I know it's a lot of content, but hopefully you find this package useful. And again, please, please, please reach out if you run into any issues. Thank you very much.